whatever time of the day it is and whatever part of the world you are. You're very welcome to join us at the Institution of Structural Engineers for a lecture on the structural engineering in a live operating environment at Central Station Metro, Sydney. My name's Matt Byatt. I'm a past president of the Institution of Structural Engineers, and but I think that's enough about me. For those of you that aren't used to Workcast, there is a chat and discussion box that you will see on your screen. If you have any questions regarding the topic, feel free to type them in. We're expecting a large audience today, so we may not be able to get through all the questions, but the speakers will endeavour to do as many questions and answers as they can. If you have problems connecting, there's an email address, events@IStructE.org, and if you message that email address, there are people there waiting to help you. Hopefully you won't need it though. To the institution's best knowledge, copyright permission has been provided for all material shown, and this broadcast is therefore presented in good faith. Hopefully you can read the rest of the copyright notice on the screen at the moment. And without further ado, I would like to introduce you to our speakers. We have Michael Czerniawski. I've got that right all the time and then I get it wrong. Sorry about that, Michael. So Michael Czerniawski, who is an associate structural engineer at Aurecon with a passion for integrating architecture, procurement and construction. He leads Aurecon's Modern Methods of Construction Specialist Group. We also have Tony Lavorato, who is Aurecon's Design Director for Structures, and he brings 40 years of experience in complex transport-related precincts. He's led the design and the design management of major projects, including Central Station, Main Works, Pitt Street Station, and significant heritage structures such as 5 Martin Place and the ACT Law Courts. Tony's award-winning career spans diverse structural challenges from intricate heritage underpinning to tall buildings and major transport infrastructure, establishing him as one of the industry's most respected design leaders. So without further ado, I will pass you over and enjoy the presentation.
Thank you, Matt. Thank you for the opportunity to present the structural design of this very complex project, Central Station Metro. Michael and I have worked on this project from the early concept stages all the way through to completion. It's rare as a structural engineer and a structural designer that you can have such an influence on the design of a project and ultimately how the end users interact with the built form. We'd like to present the story of how this design evolved to meet the various complex challenges. In order to appreciate the scale of the project, we've superimposed the extent of the Central Metro project over King's Cross Station, so you can get an appreciation of the size. The project had a footprint of approximately 300 metres by 200 metres and is located under, over and through the existing live and operating Central Station. We want to step you through some of the background, the challenges, the process that informed our structural solution. Due to the time, we really have to limit the presentation to just a few of the many design packages for the various areas of the station. Firstly, an introduction to the heritage Central Station itself, and I'll hand you over to Michael.
Thanks, Tony. So Sydney Metro is the largest urban rail infrastructure investment in Australia's history. So by 2030, we'll have 4 metro lines, with 46 stations and a 116-kilometre standalone metro rail system. For this project, excavation and structural works needed to be complete in the approximate 2-year timeframe, with quite a long and detailed fit-out, testing and commissioning phase for the project. Here it is. This is the project here. So Central Station Metro Works will deliver the most significant upgrade to this station in decades, which is an integral part of the New South Wales government's Metro and Southwest project. It had a capital expenditure of about 955 million AUD, which is 500 million Great British pounds. This project was delivered on budget and actually ahead of schedule, which I think globally is something that's rare for major infrastructure projects, or a bit rarer than it should be. Tony and I are representing the broader team, and we're just two of the many people across many companies who helped bring this project to life. I think this project created about 5,500 jobs. So 2 out of 5,500, but I think we did make an impact on the end outcome, which is amazing. The contractor was Lang O'Rourke, and our partners were GHD and Atkins. Oricon and GHD delivered the detailed design for all civil, structural, building and rail services engineering. And the architects were Woods Bagot, McAslan and Partners, and GHD. The scope of the works included excavation and construction of the new metro platforms, 27 metres below the existing platforms 13 to 15, shown in green, a new 19-metre central walk concourse from the new eastern entrance on Chalmers Street, shown in yellow, and the revitalisation of the grand and northern concourse entrance on Eddy Avenue, which is shown in blue. 98% of all Sydney trains stop at Central Station. As the only underground metro station in Sydney to be erected integrally within a live environment, maintaining operability of the rail interchange at all times during construction, and minimising disruption to the 270,000 daily commuters were the fundamental design drivers here. This was open heart surgery on Sydney Central Station. Not only was Central Station Australia's busiest railway station, but it's also a landmark. It contained the original Sydney Railway Company grant on which the first station and yards were opened in 1855. The Sydney Terminal building featured in this photograph was built in the early 1900s, with the clock tower added later in the mid-1920s. The site fabric contains evidence of New South Wales' first railway construction, reflecting the evolution of railway technology from steam to electric, and is home to several heritage buildings, such as the Sydney Terminal Building, Central Electric Building, and a warren of legacy pedestrian and heritage tunnels that you'll see in a second. And if I can draw your attention to the bottom right of the image, you might even be able to spot a horse and cart. So before we dive into the engineering, it's worth remembering that Central isn't a blank canvas. It's 170 years of layered infrastructure, and we're just adding another chapter to this book without stopping the story. So Central's a multimodal link of rail transport. It's the convergence of light rail, heavy rail, and now the metro. And it's in the heart of Sydney's central business district. So you can see in this photo here, and due to the site's constrained inner city location, access was a real challenge. You can see the Harbour Bridge and Opera House in sort of the top of this image here. This image just shows the completed project, where we're heading over the next, say, hour or so. You can see there's 23 tracks of terminating and through rail, with a further 4 now underground, both with heavy rail that was existing and 2 metro tracks. On Central, constraints weren't the background noise, they were the governing locates for us. So keeping the station operational, celebrating the heritage, the tunnel boring and staging, the logistics, these tight possession windows. Innovation didn't come from removing constraints, it came from aligning around them. Constraints really bred innovation for us. As Tony walks you through the structural responses, I'd just like you to think about which constraint was governing each decision and how those constraints actually improved the final solution. So I'll now hand back to Tony.
Thank you, Michael. You can see on this this slide some of the constraints around the physical location of the site. So we have the light rail, which goes around the north and the eastern side of the site. We actually had an adjacent Eastern Suburbs railway line, you can see in purple there, which is an underground station immediately adjacent. The green suburban lines, those suburban lines operate pretty much 20 hours a day, 365 days a year. Then you have the orange intercity, they're operating intercity regional platforms. They take the trains from Sydney out to the regional areas. And then on the other side, you've got the bus pick up and drop off. So it's pretty much constrained on all sides. When you superimpose, you can see from a constructability point of view that there's no access. There's pretty much no access on all sides. But so part of this project, or part of the enabling works for this project, in order to meet this challenge, a separate contract was let to build what was called the Sydney Yard Access Bridge, which you can see down the bottom of the slide in yellow. That provided the only access to the construction site, which was a bridge, and you can see in the photo in the top left-hand corner. In addition to that, the whole of the central station was overlaid quite a complex network of underground pedestrian tunnels. Some of them going back to the original construction of the station. And you can see in blue the actual where the tunnel boring machine. So they're where the actual tunnel for the twin metro lines traverse the site. So, as Michael explained, there was 4 main work fronts, and all of them had to be coordinated in terms of access and the ability for everything to be constructed from that one access point. It's also important to understand how the wider metro project was procured from the government. So there was 3 main packages, and I've tried to describe it in this sort of in this cutaway of the main metro box. You can see the actual tunnelling systems engineering, or the actual tunnelling and excavation, was one contractor package called the TSC package. There was also a line-wide package, so there's a separate contract let for what we called line-wide, which is basically the fit out of the tunnel. That's the tracks or the communications, the ventilation, the fire systems of the tunnel, and the communications. And some of those, some of that equipment and some of those control rooms were actually located within the station itself. And so there was a great deal of interface between those two contracts. And then there was the station fit out, which is basically, there were seven metro stations along this particular line, the City and Southwest. Central Station being one of those 7 stations. The tunnelling package was let earlier, but at the end of the day, the tunnel systems, or the TC systems, the line-wide and station fit-out, were concurrent projects. So they were all operating at the same time, and there was a huge amount of interface required. I think it's important also to understand some of the, again, talking about some of the constraints, is around the geotechnical constraints. So we fortunately had quite good sandstone underneath this site. So the site was overlaid by some fill in pink, and then some of the residual soils or residual clays. underneath it down to very, very good, very hard sandstone. One of the things about sandstone, which I'll talk a little bit further in this talk, is it does contain what we call locked-in stresses. So if you excavate Sydney sandstone, it will want to relieve those stresses and tend to move the actual face of the rock excavation. There was also a vertical inclusion, what we call a dike, which traversed through the centre of perpendicular to the direction of the metro box, which is a 3 or 4 metre wide inclusion in the sandstone, which was highly weathered material that went very deep, which means we had to bridge that. This is an image from our structural model. It's really to give an appreciation of the quantum of the project. I want to really start to initially focus on the design of the main metro box, which is the main element that was located under the existing interstate tracks 12 to 14. So these three platforms or tracks were the only platforms that were actually closed for the duration of the project. But all other tracks and platforms adjacent to the metro box were not closed, kept open. So what I've shown here is a section through what's called the reference design. So when the government procured this project, it went out to various contractors in a design and construct contract, and they were provided with a reference design, the design that was produced by the client's own technical advice team, to give a sort of an indication of what they feel would work. So contractors could either price that as their methodology or were encouraged to come up with an alternative. But one of the things that's probably very important to appreciate is some of the timing constraints. So you can see our consortium, which was Laing O'Rourke, were awarded the contract, but they weren't allowed to excavate below that line, that red line there, which is RL 3.655. The reason being is that the tunnelling contractor was still tunnelling underneath there. So there was a time delay, and the tunnelling contractor would then extend the tunnel boring machine through to near the actual harbour where it transferred to a different type of tunnelling boring machine. The tunnel boring machine had conveyors which took the spoil out from the cutter head all the way back several kilometres to the first station, which was at Sydenham. So even though the tunnel boring machines may have passed, it was still a live operational environment in the tunnel itself. It had people walking through it, and the conveyors were still taking spoil out. So they weren't allowed to excavate below. But on the other side, they had a time constraint that they had to deliver some of these rooms within the station to the line-wide contractor to enable the line-wide contractor to fit out the rooms. So you have a project where you're awarded the project, but you can't start for quite a while. But at the other end of the program, you had some very very hard and fast dates that you had to meet that had some commercial implications if you didn't meet those dates. So as a underground station to be erected integrally with the live environment, minimal disruptions to the daily commuters, that was a fundamental design driver. The reference design, as you can see, utilised pretty much a top-down, a bottom-up construction where you excavated down and then constructed from the bottom up, which means you had to wait for the tunnel boring machines to go through. What it achieved, There were no columns, no central columns in that upper area which was the main concourse. So they had some very large beams that spanned across the entire width of the concourse. And then underneath you can see those see that structure which hung down above the metro platforms at the lower level. The whole structure spanned across, and it did restrict some of the head heights, especially in the concourse. And we also had some beams that permeated through the atrium void as well, which interrupted some of the architectural sight lines. So we outlined some of the challenges, some of the physical challenges on site and some of the programming challenges. And we had to work collaboratively with the team to really unlock those program constraints. And I just want to sort of outline that in the next few slides. Looking again at the scale of the project, and given that the access is only at one end for material workers, and also that's in and out, so that's spoil coming out and material coming in. As Michael mentioned, in this very collaborative environment, when you've presented with these challenges, you start out with a lot of what ifs. And I think some of the solutions that were thrown around, one that really we started to look at seriously was, what if we try to support the structure above that RL 3.655 level to enable us to at least build that top bit and hand over those rooms earlier. So what it meant was introducing these raking struts and introducing some central columns in the concourse area. The raking struts then came down and were constructed above that RL 3.655. So what it meant is that they could basically start straight away and decouple that long excavation process and the construction of the metro box from this type program. Now, it created, when you compare the reference design on the left to our solution on the right, it did create some other benefits. Because it became a three-span structure up at those top levels, it enabled us to reduce the size of the structure. We didn't have to span across the 25 metres, so the structure became less. We also were able to step that upper platform level, the country league platform level, to make it three-span, and we were able to raise the level of the main concourse. So you can see we increased the ceiling height by at least 1.5 meters. We're able to bring natural light in now, all the way filtered natural light, because we were able to put a lot of skylights up on that level. And we're able to bring filtered light now down, all the way down to the metro box level. And reducing the quantity and program had enormous benefits from a sustainability point of view. So the client loved it. Our architectural colleagues loved it. So in the tender offering, and these are some comparative photos, we presented this design to say, here's an alternative, and the images on the two top slides were presented as part of the tender response to say, here's what we can achieve. And the photos below are the actual photos taken not long ago. So you can see they were able to deliver on the promise of making it a much freer, open platform and bringing a lot more natural light down into the metro box. Given the solution was accepted, then we needed to work out how on earth you put in raking struts in a top-down construction method. I mean, and this was the real challenge, amongst others. So I've stepped through. I was going to show a series of 4 slides to step you through a timeline of how it was constructed. So you can see the stage 1. Traditionally in top-down top-down construction. You put plunge columns down, so you construct the columns. You put steel structures down that eventually get concrete encased. The steel columns provide the temporary support for the first intercity track and platform slabs. So stage 2, the intercity track and platform slabs were constructed. Again, remembering this is all coming from the Sydney Yard Access Bridge. So the trucks had to come in and come out all through that one bridge and along the 250 metre long metro box. Then the stage 3 is the construction of what's called the main metro concourse level. Stage 4 was the excavation down to the RL 3.655 level, and you can see we left a pillar of rock in the centre where the plunge columns were still embedded. Then stage 5, we then installed the foundations and the raking struts. Stage 6, we then between stage 5 and stage 6, a very important stage, which is the jacking process, where we actually, at the base of those columns, there was a series of hydraulic jacks. So we jack, and I'll talk about that in a little later on. We jacked the structure up and then remove the plunge columns. Then we started to construct some of those, what we call some of those basement levels, which contained a lot of the back of house plant and equipment rooms. And you can see in yellow in the middle there, they actually contained some of those rooms were the rooms that had to be handed over to the line-wide contractor. Then stage 5, as soon as we were at the point at which the tunnel boring machines were decommissioned and they were handed over from the TSC contractor to Lane O'Rourke, then they could excavate down to the metro platform level and the metro track level and construct the remaining basement levels. By the way, those levels, you can see those three at the bottom levels, they are actually suspended and hung from the concourse levels. So if we revisit the program, you can see what our solution did was enable the contractors to start early and hand over those rooms to the line-wide contractor, and basically decouple the program from the very high risk program constraint, and the byproduct being a much better architectural and solution. If I then quickly want to go through the actual raking columns and how they were installed and how they were jacked. So I just pause for a minute and explain the reason why we wanted to jack or hydraulically jack these columns. So the concourse level, which is the level at the top there, was suspended on rock, suspended across and supported on the temporary strut columns, the temporary plunge columns. When we constructed the actual struts, they were cast in situ concrete. They did tend to shrink away a bit, so we were left with a gap at the bottom. We also wanted to make sure that there was a full load transfer before we removed the plunge columns, to make sure that there wasn't a sudden movement or sudden at the load transfer there was a movement that we wanted to avoid. So what we did is we put at the base of the column, you can see in red, we put a couple of hydraulic jacks within a steel shoe, what we call the steel shoe environment, where the jacks could be slid in, they could be jacked up. Then there was a whole series of cells that were then grouted, and then when the grout went off, we were able to remove the jacks and then do a subsequent grouting. The staging in the grouting had to do with at the point of the load transfer. So when these struts were jacked, it happened at night. There was no construction activity above, all within the grid that was hydraulically jacked that particular night. All the load was removed. equipment, dead load, any materials that were up there, construction materials were removed, and then so they were jacked. The grout went off in the matter of a few hours. So then we were able to release that particular area for construction activity. So this jacking operation was done at night. As I said, construction activity stopped, but by the next day they were able to continue. And you can see the sequence there in a bit more detail. Now you can see on the left the actual plunge column with the construction of the strut with the reinforcement in place, and you can see with the cast in situ solution, we had a plate that was cast in at the top of the node. We had reinforcing bars threaded into that to have that continuous operation, continuous design load transfer. Again, this is the ranking column with the formwork and the typical formwork, which was, as I said, the frames were done in sequence. So there was 18 grids. So these were constructed in sequence, and then so the excavation can follow that in sequence. You can see the close detail of the jacking assembly, or the shoe we called it, and you can see on the right hand side the actual grouting cavities, and I think you can slightly see in the center photo that there was some holes there that the grout was then poured into. Being it was at an angle, it was quite easy to pour the grout in there, very flowable grout, and I was able to fill those particular cavities. On the left hand side, we did a trial fit of the two halves of that jacking assembly in the factory. Given that it was at an angle and it had to transfer shear as well as axial load, we machined the perimeter, the outside of that upper shoe and the inside of the lower shoe to make it pretty much a very extremely tight fit. I think the tolerance was a millimeter. You can see now the photo of the plunge column still in place with the raking column, and that node at the top where we had the plunge column going through, and we have the reinforcement and stressing for the concourse level in both directions, and then we had that very heavy reinforcement for the column. All that had to be coordinated, and the contractor actually did a trial in a warehouse somewhere. They did a trial sort of mock-up of this to make sure everything fitted before they tried it on site. So this is the arrangement just prior to the jacking. The struts in place, the plunge columns. You can see the concrete encased, but you can see at the top of the plunge columns that there was you can see the steel from the original steel plunge columns, and they had at the underside of that node we had two plates bolted, so we could unbolt those when we go through the jacking process. So again, just a summary of the actual jacking load transfer, what we call the atrium load transfer. The process was we decided to prop one grid at a time. These grids were at 15 metre centres. We decided to sequentially start at one end of the box, and the northern end of the box, and put the jacking process through to the south. So the process was we did a lot of we basically did on the night we did an inspection of the whole deck to make sure that there wasn't any load that we hadn't accounted for. We loosened the bolts at the underside of the plunge columns, at the underside of the interface of the plunge columns to the underside of the concourse level, and we then did the actual stage jacking the actual jacking was done in stages, 20%, 30%, 50%, 75%. We reviewed the data at each stage. We stopped, reviewed the data. We then had survey markings to make sure there wasn't any movement that we weren't expecting. And then we basically grouted and then as I said, grouted, cut the plunge columns and then handed that particular grid over to the contractor. You can see here some of the staging. So the initial survey markings were installed. There was station theodolite and survey markers installed on adjacent grids plus the grid that we were actually jacking. And we had survey markers and movement gauges at the actual jacking assembly itself. Unbolting of the bolts prior to jacking, and we were ready to do the load transfer on that raking column. First, this was that photo on the left was taken actually on the first grid. There's quite a lot of people there on the first grid. There was 18 grids. So the first one drew a lot of attention. I've got to say, by the last grid, there was probably only 2 or 3 of us down there, but at the first one, there was quite a lot of people, interested parties, to observe it. You can see on the right-hand side one of our engineers reviewing the data during the jacking. So it was a live environment where we had to make sure we were monitoring it in real time. Again, you can see the plunge on the center. You can see a close-up of that plunge column with the top connection. Interestingly, we had all the survey markings. We actually had strain gauge. We actually put strain gauges on the foundation system as well to make sure that load was coming concentrically on that foundation. So we had a great deal of sophisticated measurements. During that whole process, I took the old school approach. So I stood there with a pair of binoculars, and I was just looking for that gap between those connection plates, because I think sometimes you can have all the data, but you really need to have that physical telltale that the load had been transferred. And I was just trying to observe, and we did observe on most of them that you could actually see a small gap between the connection plates, and that told me that the load had been transferred. Once that occurred, they actually demolished the top of the plunge column. So they actually cut the plunge column away, and then you can see the plunge columns being removed, and then the system operating as a full strut and tie system. Vertical load coming down the strut in compression, and that concourse member also acting as a tie member in compression as well. This is some images of what it looked like when we then started to do some more detailed excavation. So you can see the center photo. We can see the base of these struts. You can basically the underside of that. That's the level 3.655. So this is at the point at which it was handed over, so they could start excavating down below that level and starting to construct some of the hanging elements for those lower basement levels. And you can see the section on the right-hand side, and you can sort of see on the left-hand side a lot of the you can see the struts now starting to be hidden behind the plant room levels. So when you walk down there now, you actually can't see any of this. It's hidden below the well behind the main metro station. Some more images just of the sort of operating environment that that occurred. All the excavation that occurred below had to be lifted out on through the mole holes up into the top deck with trucks. So then took the trucks out over the Sydney Yard access bridge. So you can see that sort of operation occurred throughout the whole process, continuously, and you can see that photo on the right hand side. I think that that actual clamshell crane was actually purposely built for this particular project, removing the spoil up from these mole holes through the raking struts, through the concourse level up to the intercity platform level. And just bearing in mind in terms of program, this at this point here, with the original scheme, they probably would have been just excavating down from the top at the similar stage in the project. So I think now I just want to hand you over to Michael. We've got a video that
So Tony mentioned, but basically this solution saved 9 months on the program, and that's not just 9 months on this aspect of the program. That's the critical path program saving 9 months. So there's a simple solution structurally, but actually with big impact on the project. So you can see here as excavations going down, you saw the tunnel linings being broken out because they line the machine as the tunnel boring machine goes through. Yeah, like Tony mentioned, 280,000 tons, which is about 100 Olympic-sized swimming pools of material pulled out from these mole holes in 2-meter cube batches with this clamshell. I think it was a Liebherr 30-meter clamshell. And here you can see that's the metro line once it's built. Nice views of the tunnel leading out. And the hanging steel there that you can see on the left and right of image, that's, I think there's about 400 tons or so of hanging steel that all hang back up at that concourse level. So it's a fair bit of material going through there.
So one of the other challenges we had, probably the biggest technical challenge we had, was how do you do a top-down construction in this rock with the stress relief? So one of the main issues we had was the size of these plunge columns. And in order to reduce the size of the plunge columns, we then had we utilised the lateral restraint provided by the concourse level, or the levels going down, so that as we excavated down to reduce that effective length of the plunge column, we said, well, let's use the concourse level to strut to provide lateral restraint, which means the lateral restraint had to go somewhere, and then it went to the sides. So we had it constructed hard up against the rock on the side to make sure if it wanted to buckle, that it was restrained. Now the problem we had is that when you excavate in Sydney sandstone, you get stress relief. So normally in any basement building in CBD of Sydney, you excavate down, the aspect ratio is usually 1:1, 2:1. So you've got a rectangle, and there's a stress relief in the rock. When you take the overburden out, it's that Poisson's ratio effect. It wants to release, and it releases that stress, and it does that by moving in. The sides move in. And rough rule of thumb, for every metre you go down, it's roughly a millimetre that comes in. So 20-metre excavation, you expect the sides to come in 20 millimetres. Now, in the traditional bottom-up project, it's never an issue because you excavate down. By the time you come back up, that stress relief usually occurs in the first 30 to 60 days. After that, it pretty much is relieved. So if you excavate down and then construct back up, by the time you get back up, it's not an issue. It has occurred. Here, we're excavating down. So we've got that concourse level that's used, which is not the top level, the concourse level, which is the second level down, providing lateral strain to those plunge columns. But at the same time, as we excavate, you're getting that delta coming down. So the solution, and then we had a further complication because we had two stages. So what happens is the first stage we had that delta 1, so that rock moved in, and then we had that second stage excavation. We had the delta 2, the bottom bit came in, and then it dragged the top bit as well. So at the top we had sort of delta 1 plus delta 2, and at the bottom we had delta 1. So how do we accommodate this? We want to strut to the rock, but coming in 20, 30 millimeters, we would have crushed the concourse level. So the solution we adopted was to install at each grid point, the whole of the concourse level was constructed with a 20 millimeter gap to the side rock, with the exception at the actual main beam, which formed the top strut of that strut and tie structure. And what we did at that point is we put hydraulic jacks in. And the purpose of the hydraulic jacks is that we put a load. We put oil in the cylinder, push the jack up against the rock. But what we managed to, working with the jack suppliers and installers, is we had a predetermined limit. So what happens with stress relief in rock is it can take two forms. It can take an elastic form where it slowly comes in because there's an elastic release of that stress. But when you have bedding planes in sandstone, because sandstone's a sedimentary rock, it can slip. So quite often, you come in there, overnight it'll just slip. And so we wanted to make sure that when that occurred, if there was a sudden movement, if there was a load on the jack above a certain amount that we wanted to, a certain trigger point, that jack would release the oil in the cylinder, and it would come back, and then let that movement occur, and then come back out again. And all this movement was monitored, and we had real time monitoring. Myself and our lead geotechnical engineer would get text messages to say something had happened, so then we could have to then address it and make the decision of when we would then put the jacks back in place. So this is the detail. You can sort of detail in the top right-hand corner. You can see the beam, which is about 1 meter wide, coming through. You can see the gap around the side of that. So it's that, and you can see the jack installed. It was a flat jack type jack, but it was installed vertically. You can see the detail on the left-hand side. The salmon area indicating the fixed concrete, or fixed concrete that was poured up against the rock, and you can see that ability to move that, allow the whole structure to, well, allow the rock to move, but not to damage the concourse level. These jacks were kept in place pretty much until it was excavated all the way down to the platform level. Then when the movement had stopped, the jacks were removed, and that whole interface, including the jack pocket and that whole 20 millimeter gap around the perimeter, was then grouted. So I want to now hand you over to Michael, who is going to talk a little bit about another main area, which is the northern concourse entrance.
Thanks, Tony. So welcome to the front door of Central Station and New Metro. I was fortunate to be the structural package leader for this part of the project. On the left-hand side, you'll see the Heritage Central Electric Building, built in 1930. This is oversailed by the new feature canopy roof. The canopy roof lands on the intercity balcony on the right-hand side, which is a 10-meter exposed concrete cantilever with an organic form. And just under the balcony, you see the link to the new metro box where passengers go and access the metro platforms 27 meters below ground on the longest escalators in the southern hemisphere, which is cool. So it's one of the busiest confluence points in the station, and the architectural aspiration was to respect and celebrate the surrounding heritage and create a really light filled and grand and intuitive space. So you can see the references on left hand side. It met the functional requirements for a pedestrian connection through the station and a thoroughfare. However, the design limited the aspirational performance, I guess we call it, of the lower concourse um, as it obscured some of the view as you go up of the roof, and it reduced some of the natural light, an opportunity for natural light to get through. Um, it also had an underlying column grid, which sort of made the space a little more cluttered. So our win intended design proposed cantilever intercity concourse, pull that concourse back to express that heritage building and achieve a column-free zone under bring light all the way into that part of the station. I mean, the left image isn't a flattering image of the reference design, but yeah, you can see here the a bit of the difference in trying to create this really grand entrance. This slide just shows the main egress paths through the station. This particular aspect of the project is through one of the busiest pedestrian thoroughfares. Just quickly touch back. So natural light, maximize that in the subterranean areas, help with like creator orientating and intuitive wayfinding through the station. So the northern concourse canopy, it's approximately 40 meters wide, 80 meters long, 12 meters high. It's 330 tons propped cantilever steel structure with curved aluminium cladding and 21 large kite-shaped skylights at regular spacings. So the intent was clear. It's not just weather protection. It's designed to really create an iconic front door to a world-class metro. Central was to become a destination in its own right, not just a place that people pass through, but a place people stop and pause. So we spent a lot of time listening. The brief was clear. We needed to create an iconic front door to the station. The roof interfaced directly with multiple heritage structures. It supported some of them. It straddled others. We needed to also reticulate 2 full cable trays of services from these heritage buildings and the other parts of the station through the roof down into the metro box, linking in. And we needed to allow for future expansion of this structure into the future. And we had to align with irregular platforms, which were 8 to 13, platforms 8 to 13, and yet create this regular space skylight in creating a space that really was disconnected prior to this project. So we felt we understood the architectural intent, the services constraints, then constructability entered the room. So feedback from the builder, fabricator, riggers was clear. A stick build solution here would take 4 months. We knew a stick build solution wouldn't work, but it was great getting that feedback. The station had to remain fully operational, so site time had to be minimized. Temporary works reduced because we can't leave any temporary works that obstruct commuters in the morning. So we did a lot of the work in night possessions, these 4-hour windows, which when you count startup time and handover time, like it's probably 3-hour window to actually work. Logistics and craneage limits became critical here. The structure didn't just need to work, it needed to work fast. So as you may know, in live rail infrastructure, there's only select periods where you need to undertake the majority of the construction works. So for Central Station, there's a real emphasis on the speed of on-site assembly. So the majority of works undertaken in those small windows, those 3-hour windows. And you can see here the primary structure shown in red. These sit at sort of irregular spacings from 7 to 13 meters because of the irregular platform geometry and to avoid impacting commuters. But the architectural intent needed regular spaced skylights. So through computational engineering, we rationalized the secondary structure to maintain consistent skylights and a soffit geometry despite that irregular frame. And each of these pre-assembled modules that you can see in pink, blue, and green had all of the glazing in, the lighting, the services, and most of the soffit cladding. And they weighed up to 9.2 tons, which was just basically the limits of what you could transport and what you could lift with the crane at that radius. So on site, to make it fast, we simplified all the connections. So each panel just had 4 simple connections of 2 to 4 bolts. And through modularizing this and prefabricating these into stable elements, it was probably extra 20% on tonnage. But really those benefits and time on site was really what made this a solution that was optimal for this project. And at each stage, it needed to be stable so that you could hand it over. You could hand it over in the morning and commuters can work through. And it was fast. So you can see that in the space of about 7 days, it's almost half of the roof structure that was complete. Yep, so here you can also see, just sharing a quick time lapse. So it was fabricated locally, so in Kurri Kurri, which is about an hour and a half from the project. We did a full-scale pre-assembly in the fabricator's yard. That's to make sure that everything fits like clockwork, and really to test whether or not it could be built in this 4-week period that we had of just these night possessions primarily. So this time lapse kind of shows how modular construction can be adopted at scale here. And I think the interesting thing is you want to get tolerances. Tolerances are very interesting. You don't want to have too much that the structure can start to build the structure out of position because you've got too much plane or the connections. So you want the right amount that lets you have that adjustability, but still keeps the structure in place. And basically, the builder said this went together like Lego, and that's one of the greatest compliments I've had as a structural engineer. Tony, I've lost my cloud share. Can you click the next slide, please?
Oh, sorry, Michael, we can't hear you.
Sorry. Yep. We're starting to run out of time, so I'll just go through just very briefly on this, which is the precast colonnade that supports the roof. So the canopy was supported by this 80-meter long, 6-meter high precast colonnade. It was installed in a 32-hour possession window at night without temporary works, so pedestrians could access those platforms. It's a really good concrete finish. Tony, would you be able to click next? Thank you. So it was a precast in situ stitch system. It had to behave monolithically because it takes the moments from the cantilever roof or the prop cantilever roof, and keeping it monolithic improves efficiency. And really, it's just governed by how big of you want to, as with most precast and prefabrication, you want to have as big of an element as you can lift and transport installed. So you really want to limit it, and that's what governed the size of these modules. So the geometric considerations were further complicated with that need to remain operational. You can see this is one of the busiest commuter pathways. This was during construction. Most of this is built at this stage, but you can see these are a busy part of the station. So the cantilever slab that you can see on the left, that was originally planned to be built in 16 discrete pours so that you could block off only parts of that station and that commuter egress pathway. In the end, it was, I think, about 10 pours that they did that in. Next slide, please. So you can see this is just sort of the main confluence point and link into the metro. So this is just a section through that 10-meter cantilever. You can see we've got these services channels in the bottom of the soffit. And we really worked to rationalize the geometry because it started with a lot of double curvature, and we just tried to limit it to single curvature as much as we could so that it could reuse aspects of the formwork. And you can see here that there's the left is a fiberglass mold, and there was sort of a bespoke double curvature element at the top of the columns. And on the right, you can sort of see that we used CNC. It was basically CNC cut formwork that was reused along the slab. And they stored all the aggregates on site for each pour to keep color consistency. And we often say a structural, well, I hear as a structural engineer, architects and others sometimes say that, you use sides, beams and slabs. That's your job. And yes, that is our job. That's true. But on projects like this, the structural engineering becomes a link between architecture, procurement and construction. And we can be the discipline that really turns aspiration into something buildable. It's a little hard to see here, but that's a before and after of that part of the station. So it has really changed. And on a personal note, this project is very close to my heart because every day for university, I went through this station. And I remember the first day I went through the station, I stopped in my tracks to admire this structure here, which is just adjacent to the new roof. And I sketched it out, and I even got to uni late that day. And then some 15 years later, I remember watching a commuter stop, take a photo of the roof and discuss with their friend some of the things that may be happening behind the scene on this project. And it was a real special and proud moment. And I hope everyone listening has a moment like that. And I'll now hand back to Tony to just talk through the Devonshire Street Tunnel underpinning.
Thank you, Michael. Devonshire Street Tunnel. This is a tunnel. It's actually behind. It's in front of the ticket line. So this is a tunnel that connects pretty much the eastern side, all that area on the eastern side of the central station, which is called Surrey Hills, to the western side, which is called Broadway. And Broadway contains quite a lot of universities. It contains, it's the location of our main broadcaster, ABC. A lot of commercial space, a lot of residential. Similarly on Surrey Hills, it's a bit more residential. But the only way to get from the eastern part of the city to the western part of the city is via this tunnel that goes underneath Central Station. So it's not part of the actual station itself, but it is. Well, it's physically part of it, but it doesn't form part of the operations. But it open all 24 hours a day. It is always quite packed. It's not a very nice tunnel, but the main thing about that tunnel is that it just had to be kept operational. The reference design had a 2-week window where they would shut the tunnel down, where you could come in and construct whatever you needed to construct and underpin and then open it. We looked at this, and when we looked a little bit closer at the tunnel, and that's the actual tunnel on the left-hand side. But when we looked at the way it was constructed, you can see the original drawings there. It's constructed very close to, I think it's 16 inches in the old scale, but I think about 400 and something millimeters below the track level is the top of the concourse, top of that tunnel, very close to the operating tracks. Then you can see what the way they constructed it was. You can see on the left-hand side, it was basically constructed on piers. So the elevation, you can see these arches onto piers. But what was really interesting and what it was quite concerning to us is that what was under the tunnel, which was I call this the umbilical cord between the west and eastern side of Central Station. What you have is the main 1500 diameter stormwater line. You've got the main 400 millimeter diameter, which is the old clay pipe sewer pipe. Then you have Ausgrid, which is our energy supplier as well. So the main power that went east to west all came under this tunnel. So we took the view that if we could come up with a way of not excavating this, we would remove an enormous risk of damaging any of these services. So what we wanted to do was basically, and you can see probably on the left-hand side, we had to, whatever we needed to do to that tunnel, we needed to span across because the actual metro box went underneath it. So the solution we come up with, which you can see on the right-hand side, is to actually underpin this tunnel, get down to the rock level, put some horizontal bores in there, and basically cup the tunnel. So what we did is we did not disturb the area underneath the Devonshire Street tunnel at all, where those services were, nor did we disturb the actual tunnel itself, so people could operate. So we didn't go with the shutdown. So what we did is we decided to, as we were excavating down, remember those sections that we had, those various excavation stages, we would pour the first thing we've done, there was a whole series of secant pile walls that held the material temporarily. And one thing I've got to say is this was constructed in a cut and cover method back in the beginning of the back in the early 1900s. It was open, cut and cover. It was then constructed, and it was backfilled with basically sand. So not only does it contain all these services, it's from a hydrogeological point of view, it's a main point of which in-ground water goes from west to east or east to west, depending on where the main gradient is. So it was very heavily water charged ground as well. So again, we didn't want to disturb it. We went down in stages, and then you can start to see. So they're the secant pile walls on the left-hand side. You can see on the right-hand side the underpinning walls that we came down. They were then vertically, conventionally reinforced vertically, and we had stress bars horizontally. We had that. You can see that castellation of the interface to make sure that the shear transferred adequately across that. You can see the horizontal boring that was done in that class 2 sandstone, very good competent sandstone. They were poured, and then the final level came down. These horizontal board piers or horizontal circular beams, you can see the reinforcement came out, were then tied into this wall. And you can see on the right-hand side, the finished product. So up the top, just above the top of the boom of that excavator in the distance, you can see the Devonshire Street tunnel that traversed the site. So that whole operation was done while we kept that tunnel operating. So people walking through that tunnel night and day probably had no idea what was going on underneath. And probably the main thing we kept operational is all those critical services infrastructure, which we kept damage-free and operational. I just want to go back to this photo that Michael sort of presented, which was, and I started the discussion by saying that it's rare that a structural solution has such an impact on the way people interface with the building. So on the left-hand side and the right-hand side, it's pretty much the same view. So you're looking on the left-hand side, you're looking from the northern concourse, you've got the cantilever slab above, you've got that Michael's magnificent roof over the top of you, and you're looking down into the metro concourse level, and from that level then you take the escalator all the way down to the metro box. And what you can see there is clear sight lines. And at the base of that, where that arch springs from the top of those circular columns, you can imagine if the reference design would have had horizontal beams at that level, which meant you couldn't see down there. And similarly, on the right-hand side, try to imagine those beams coming across at that springing point of the arch. That's a great view all the way through the northern concourse, through the central electrical building, out to the entrance of the station. So that clear sight line was a wonderful thing to achieve, and was achieved by our structural solution. and the architectural treatment of that solution. One of the things that people comment on with the natural light and with those clear sight lines is how and these splayed walls is how safe people feel walking through this space. There's no blind corners, clear sight lines, very secure place. And that's when I spoke initially about it's rare that you can link something that you do structurally to have such a great benefit to the end users of the project, more than what you normally engage to do, which is to make sure the building doesn't fall over in an earthquake or takes all the loads. I'm just looking at the time, and we've probably got a few minutes still left over. There are some of the, we just want to quickly touch on some of the, I'll hand you over to Michael to conclude, but some of the final, some of those other areas that we mentioned initially about these numerous work packages. So I'll quickly hand you over to Michael to conclude on that.
Yeah, so we're running out of time even just talking about the sections we did. So like very briefly, there was two major other packages, Central Walk and Eastern Entry. You can see here Central Walk was quite an innovative process in itself because it had to be constructed underneath the live railway. Over here, it's a 19-meter wide tunnel basically from the street level through to the metro platforms. You can see this guy kicking goals on the left. So Central Walk was opened in 2022. So the project opened officially 2024 in terms of the metro running, and but actually this station was completed early. But Central Walk was opened 2 years earlier to gain, because it provided benefits because it linked the whole station even before the metro was open. So that was really quite good that as soon as you have something that's ready on this project, we opened and gave it to the commuters. And an eastern entrance here. This basically is a new connection through to Surrey Hills, which is a busy part of the station, and you don't have to cross the road anymore in this busy light rail interchange. So it was post-tensioned, reinforced concrete generally, and there was about 19,000 tons were removed to excavate for this entrance of material was excavated. So 6 Olympic swimming pools. And then the last one is that heritage building, 1930-ish, let's say. We had basically designed the underpinning of that so that we removed 2 columns for a steel transfer beam. And the fun fact with this one is that the sandstone cladding you see in the image at the bottom, that actually came from the exact same quarry as the sandstone over. So they kept stockpiles of this sandstone for, say, future development like this. And I'll just end. Just end on video, which is basically Central Station in 60 seconds. And I just feel this project shows that, you know, structural engineering in a sustainable, livable, resilient infrastructure environment. I'm just going to give some fun facts while I've got 40 seconds left. So the project achieved a 6-star Green Star rating, which is the highest possible rating and characterizes world leadership in environmental sustainability, design and construction, as well as operation. So this was due to 38% reduction in concrete versus the reference design. So that's a 32,000 ton saving. So heaviest animal in the world, African elephant, we saved 8,000 African elephants in massive concrete. Of the concrete we did use, 51% supplementary cementitious material replacement was achieved through fly ash and slag. There was a total of 373,000 tons of sandstone excavated via 11,000 truck movements. 320,000 tons of that were used on other projects within Sydney, like Barangaroo. So that's 100 Olympic swimming pools worth of rock excavated out and reused on other projects. So 5,500 new jobs generated. Tony and I are grateful for, of course, being 2 of those. And not really a fun fact, but this was actually like a really incredible team from all subconsultants, subcontractors, and it's a dream to work on this project. So we now have 98% of Sydney trains running through Central Station, 2 new metro lines, which run approximately every 5 minutes. I'll now hand back to Matt for Q&A.